tell you what I'm doing, huh? Let's see. So this is 54.3 and 54.5. And it's going to be in that same area in the OpenStax in that chapter 36, because that's all about biodiversity and like competition and things like that. Okay, so I can just see it. Sorry about that. It has its days. It gets super curly for some days. All right, so I'm going to just start actually doing what I'm here to do, is how do intermediate disturbances contribute to species diversity? So I want to come under here. We probably should know what species diversity is. So there's actually two different words, and I'm not real sure I like the way this question's worded. I picked them a lot of times from what College Board has. This is kind of a mixture of both. So let's separate those out. So there's two ways to measure what's called diversity, which just means how much of a difference do you have. One is called species richness. So if you look at the richness, is what they usually go by. That's the word they tend to use the most. All you're going to do is you're going to go into an area and you're going to count the number of species. I don't care how much I have of each one. You know, you could have, I don't know, 1 million of one thing and 6 of another, and you still have 2 that you're counting, because there's just 2 that are different. So the richness is only the number of different species in an area. So you do not take into account how much of each you have. That is through biodiversity. So biodiversity, it's the number of species in an area and you take into account, so plus the abundance, so how much of each species. So you do look at how different, like I have this many different species, but in this particular case you could say, however, the majority of those are made up of this one. That's what biodiversity would be. Okay, I'm going to have to start coughing. Hold on. Okay, goodness gracious. I think it's my dog. I'm not sure, but my allergies are crazy. So now that we know the difference, that this is just what you're measuring, and so you have to be careful with what you're measuring, because you don't get a full picture with richness. You know, richness just has to do with, oh my goodness, look at all the different species. The biodiversity gives you better perspective of, yeah, I mean, I do have a lot of different ones, but by far there's mostly this one. So those are different. So let's talk about disturbances. So intermediate disturbances gives you the feeling that if there's intermediate being middle, there must be low level and high level. So they're saying here, if we reword this, how do just middle level disturbances contribute to species diversity? So here's the way that I think about this. When you have low levels of disturbances, you have a pretty stable place. So let's write this. So it's fairly stable ecosystem. There's not a lot of things that are shifting, changing, that organisms are having to deal with. Conditions are fairly stable. When you have high levels, pretty much all they're dealing with is change. So you've got a very unstable ecosystem. So you have high amounts, and I'm the queen of like not writing a lot of notes because I want to be able to, you know, listen and write. So this is the symbol in math for change. So there's a high amount of change that species deal with. So they're constantly dealing with all of this change. So if we do intermediate, which would be in between, you're going to either have periods where that you've got some instability, and then you've got periods where that you've got long runs of stability, or you've got periodic events that happen. So intermediate means that there's just this, I guess what you would say is it's mostly stable, and then you're going to put with some change. Excuse me. All right, so now let's draw what this looks like, because a lot of times they don't do a lot where they talk to you in words. They're very much about giving you some visual representation, and it helps me too because that's the way my brain thinks. So if I graph this, and down here on the X, I'm putting this, how stable is it? So in other words, it's going to be the levels of disturbance. So let's think about what we could do as we think about the extremes of our graph. So I could say, if I wanted to label, that we don't have them very often, so this would be infrequent. So maybe I'm measuring how often, and here would be frequent. So for this one down here, I am measuring how often the disturbance occurs. Okay, I could do that. I could also have that it's got a small extent of change or damage. Over here would be large extent. So that could be over, it's not covering very much of the area where that we're looking, and it's covering most of it, or there's a big, huge amount of damage, and here there's not much damage. So let's see what we could do here. So I could either measure, so measuring how much of the area is affected. So I'm going to put experiencing the disturbance, a small, a large, or I could have, so that's one, or it could be that you have a small amount versus a large amount. So you're measuring the amount of damage. So it just depends on how you choose to measure this. It could be time. So this has been, a long time since the event. And over here it's been recent. Okay, so 3. So you could be measuring elapsed time since the event. Now, I don't know if you're figuring it out, but we are spending a lot of time building out graphs. The reason being is that that tends to be the way that the exams run. They tend to have that graphical representation as part of what they're doing. So up here, like, how are we measuring these levels of disturbances? Well, first of all, we had to decide how we were going to label these. And so there tends to be 3 types of labeling we would have done here. This, we're just going to do the number of species. So this is just counting how many species are there. So that would be richness. So I'm just going to put the number of different species. So as weird as it sounds, over here we said that when you have low levels of disturbances, things are pretty good, like it's a stable ecosystem. So if this is number, so this would be low and this would be high, you would think that you'd have just tons, like everybody's happy. And that's not the way it is at all. It seems backwards, but you tend to have low richness when you have very few disturbances. And I'll tell you why here in just a second. Then as you start to have more disturbances, not enough to where that you're, causing stress, and most of the organisms are dealing with just nonstop change, but you're shaking things up a little bit. You start to have this increase in richness, and then when things get more and more disturbed, then you're going to have the drop in the number again. And that seems strange. So they label these 1, 2, 3. So here's what's going on at 1. At 1, because there's not much else that organisms are dealing with, you have really serious competition. So they're going to have not an interaction where they're dealing with their ecosystem changes, but they're going to really compete with each other. So here you get what's called, and I'll tell you what that is in just a second. It's called competitive exclusion. My pen's won't go. Right, funny. And this is going to limit your diversity. Like how many, where's my R go? I think I left my R out. Anyway, diversity. Over here, when you are constantly dealing with change and disturbance, most of the organisms are overwhelmed. So they're just not able to live through and survive through that level of disturbance. So the organisms, all of them, are under high stress. And you're also going to have high extinction. So a lot of them are just going to go away. They cannot survive that level of disturbance. So this somewhere in the middle, it shakes up things enough to where that these organisms that dominate with their whole competitiveness, they're having to deal with the disturbance, and it makes them less competitive. So at this point, you're going to have just the right mix to where that you're going to have enough instability to reduce that competitiveness. Trying to think how I want to say that. So let's put between species, because they're dealing a little bit with the environmental pieces. So this is the way that it works, and that's why intermediate favors higher numbers, because you shake it up enough to where that you don't end up with these just dominant pieces. Because competitive exclusion is what we talked about last time. So let's write what that is. So competitive exclusion. So when you've got two organisms, two species, that are doing the same job, the niche, the same role in the ecosystem, one outcompetes the other. They're both not there. So there's not this, oh, but can't we just live together and be happy and get along? No, not in the real world. The real world is, I outcompete you, and therefore you don't exist and do your job here. You better go figure out if there's a place where you can do that someplace else. So this is the two species. They cannot both occupy the same niche, remembering that that's the role in the ecosystem in an environment. one always is going to outcompete. One outcompetes the other. That's what that is. So this is the opposite of the whole, I don't know, Beatles movement with the, can't we all just live together? Yeah, no, we cannot. Okay, so that took a whole page. Wow. So I'm going to work on question 2 now. This is on the test. I swear I think I'm writing this all the time. That's on the test too. So talk about the island equilibrium model. So we need to break that down. Island, when you see anything island, think about isolation because it's going to be off by itself. Equilibrium means that you're going to come back to a set level. So how is this going to establish equilibrium? So how is it going to come back to a set level? And we're not going to use this figure because I'm going to draw it. So I'm going to mark through that. Of how islands that differ in size might not display great differences in species diversity. So we're obviously thinking about, with an island, how big it is, so size, but also how close it is to the mainland. So, and which is where the species come from that occupy the island. So let's think about that. So if we've got land, this is number 2. So if this is land over here, and you've got islands out here, you're going to have 2 things you've got to take into account. One is how big they are, and 2 is how close or far they are from land. So if you have, let's think what we've got as an option. So let's make this a large island, but close. And let's have a small island, but close. And then let's go out here and do the same thing. Let's have a large island and a small island that are far away. So that's what they're wanting you to picture in your head. I'm trying to think. I want to think it's Marshall who did this work. I'll have to look it up. I can't remember. So let's think about what we have here going on. So for a small island, you're going to have less area, right? And if you have less area, then you're going to have high competition because they're all living on top of each other. If you have a large island, you're going to have more space, and that'll reduce the competition. And so when I'm talking, I'm trying to write, and my head's like way ahead in my writing. It drives me nuts. So now we need to think about some words that are associated with that. When you have organisms that come to a place, it's called immigration with an I. So I always think of immigration is you're going into an area. So these are the new species that are able to come and establish themselves in an area. So along with immigration, God, no wonder English is so hard to learn. There's immigration, which, does it have one M? I'm going to look that up. Aren't there days where you just can't spell, like your brain tells you one thing? I think it's just one. Let's see. Yes, okay. That's what my brain said, but then my brain said no. Can't listen to both sides of it. So, immigration with an E, and I always think about that's exit an area. So you have to have a count of what organisms are coming in and what are going out. So what's going to happen as far as with these two. So now let's rewrite that in light of these. So when you have a small island, you're going to have less immigration because the organisms that are coming there, you have a smaller target because you're coming from another place and it's less area, it's harder to get there. Not because of how far it is, we're not talking about that, but just that you have a smaller landing spot. So you're going to have less eye immigration. And the reason it's going to be because it's a smaller target. So if you're a bird and you're being blown onto an island, you're going to have a smaller spot to land on. You're going to tend to have higher immigration, so things leaving, because of the amount of competition and the smaller number and amount of resources. So this would be due to fewer resources because there's just less space. Large islands, on the other hand, tend to be defined by higher, draw a line here so it's easy to see. Ooh, and it was a straight one too. So you have higher immigration. Okay, that's when I start cutting these crazy places on my hair. So higher amounts of organisms coming onto the island because it's a larger target due to larger. No. Okay, good. Target. But fewer organisms leave, so immigration, because you've got more resources. You've got to be kidding. Stop with all these little things. Okay. So now let's think about, so this is size, right? Now let's think about distance. So the distance from the land. Because, you know, if it's not very far to go out onto the island, it's going to be a lot easier for these closer ones to have organisms get to them. Here, you got to go travel a lot of ocean in between, and you just may not hit a target. So now let's do close. So a close island would have higher eye immigration, which would mean that, and I'm going to put 3 little dots, that means therefore in math. So therefore, you'd have higher diversity, because a whole bunch of different things could have come on there because it's close. When it's far, you're going to have a tougher time, so your eye immigration will be more difficult, and you would have fewer species. So more than likely the ones that did get there, if the resources in the space were suitable for them, they're going to be high number, a high abundance of them. Okay? So that's what they're wanting you to just flesh out in your head. But what I wanted was for you to see the picture in your mind of what they're talking about, and then walk through with the 2 different ways that we say immigration and what they mean, and think through in your head the benefits and the challenges of being far away, close, large, small. Okay? So let's do 3. So how would you expect the richness? So let's think about what richness is. Richness is just how many different species of birds on an island to compare with the richness of snakes or mammals. Well, I mean, my brain immediately goes, well, birds can fly. Snakes and mammals aren't going to do that. So what they're wanting you to speak to is that, so an island, you're going to think of it as an isolated place. So is isolated, right? And it's going to be surrounded by water. It's going to be a real challenge for snakes and mammals to get there. So what they're wanting you to state in questions like that is something super simple. They said, how would you expect the richness of birds to compare with the richness of snakes or mammals. So the answer is going to have to be either higher richness or lower richness, because I'm comparing. So when I compare the two, I would expect that the bird richness would be more than the snake and mammal richness. So I would have more different species of birds than the numbers, the differences as far as species, like how many do you have of snakes and how many do you have of mammals. So I'd have a lot more types of birds than types of snakes and types of mammals. And they asked for richness, which doesn't mean like, well, how much did you have of each bird? Nobody cares. That's not what I asked. I asked, how many different bird species do you have? It would be more than the different numbers of snake and mammal species. All right, last question, lots of words. Human evolution is ongoing. It's evidenced in resistance to disease. Oh, how appropriate this is right now. All humans alive today have descended from those, looky here, who have survived pandemics. They're talking about the plague, and everybody's talking about the Spanish flu because it's the last pandemic we really had. How is zoonotic disease a selective pressure? Okay, so we've got a couple of things we've got to talk through on human populations. So when you see something that's zoonotic, it means it affects animals. So disease, a selective pressure, well, we talked about that with the fish, right? Those with the guppies. So you have selective pressure just means things are going on in the environment where some organisms are more successful than the others. So let's come over here and put zoonotic. And then, just a second, I'm going to go find a picture here. Okay, so I thought I wanted to see a picture, but I like this better. So if you want to be really specific about zoonotic, it means that it affects animals, right? Particularly humans, but it started off in another organism and it jumped. So I wanted to show you all of the different ones that started off infecting other organisms and then, look at all this, was able to be infectious for humans. So there's a lot more than you think. The pictures didn't show it as good, so I wanted to go get you a list. So let's go here. So it's going to be affects animals, and we're naturally, so specifically, we're going to talk about humans. And then we're going to put here that it jumped. So what jumped means is this. If there's an infection that only is infectious, there's an agent, some type of pathogen, that infects, let's say, pigs. And I can be around pigs, and the pig can be sick, but that infection doesn't happen in me. I'm not susceptible because it's not a human disease. When it jumps, that means that it infected pigs, and there was some type of a mutation that now allows it to infect me. And that's what everybody's so scared of. They're scared of this jumping because the more you're around the organisms that it's actually infecting, that's why they're so worried about the bird flu, is that we raise birds. You know, everybody raises birds to eat. So there's tons of human interaction with birds. So as that pathogen, that infectious agent, changes over time, a version of it, a mutation within it, could cause it to then be able to infect humans. And the more you're around something like that, the more likely it is to happen. So this is what they're talking about with this question. So all of these diseases weren't around as far as infecting humans. So they've jumped from something else. They don't just like materialize out of thin air. They're some type of infectious agent that just didn't affect humans, and then it did. And when that happens, you have zero natural immunity. You've heard all of this because of COVID. That's what the word novel means. So when they say novel, okay, this pen is being really weird. Novel means new. And really you want to think about it this way, new to us. So when something is novel, you have no natural immunity. Now, this is not unusual. If you think about it, people get flu vaccines every year. Flu's been around for forever. I'm sure every one of us have had some bout of the flu. But when those organisms change, those infectious agents, and they become new, sometimes they're more virulent, which is the ability to cause disease, and sometimes they're less. And what's so weird with what's going on with COVID is that most of the time we are pretty sure where something jumped from. There's a lot of confusion around that with COVID. And then we're pretty sure that they're not highly virulent to begin with. Which, initially we didn't think it was. We thought that it was not going to be any worse than the flu. And for some people, they're asymptomatic and they literally don't have anything going on. And other people, it's horrifically virulent. So there's a lot of weird things about that. But what's the deal with, if you go back in time 100 years ago to the Spanish flu? How is that a selective pressure? Well, every one of us were descended from somebody who lived through it. So you get what's called a herd immunity over time, where enough people have been infected that you tend to not have these crazy spikes anymore in the numbers. But you're going to specifically answer that question is that all those that are currently around, so all of those, let's just put people now, all those people who had the disease during the pandemic and survived are going to have some type of, hopefully you can go back and say that there's a reason for that. Sometimes it's just chance, but that they survived, they're going to confer that, whatever that selective pressure selected for, so they're going to confer that predisposition or that genetic disposition to the offspring. So let me be really clear what I am not saying. I am not saying that those people who had the Spanish flu have offspring who can't get the Spanish flu. That is by no means what I'm saying. Because your children are going to have immunity that's going to be built from having experience or exposure with that pathogen. But whatever it is, maybe they just have a more robust immune system. That is genetic. But you do not pass on immunity. Now, the only exception to that is for a mother who nurses, and it's temporary, because her antibodies do move through the breast milk. So when a mom nurses a baby and she's had the Spanish flu and she lived through it, then that baby will also be immune to the flu, but not forever, because it's not their own immunity that they're counting on. It's that's been passed on to the mom, and that's a temporary thing. But I am not saying that the people who had the Spanish flu and lived from it, now I could, walk through fields of Spanish flu people and not get it because, my great-grandmother had it and lived through it. That's not what I'm saying. I'm just saying there's something about those people that they had a higher survival rate. It could just be that in general they didn't have other diseases like diabetes or heart disease, and they just tended to be genetically, their disposition or predisposed to being overall more healthy. So you want to be careful what you say and how you say it. So let's put a little note down here, and I'm going to put it in red. So I am not saying that the people who lived after the flu gave that immunity to their offspring. I am absolutely positively saying that is not what I'm saying. What I am saying is there's something about them that may make them better able to resist that infection. Okay? All right. So that's the end of that one. That's a lot. Do the best.